Okay, y'all. So today we're gonna be looking at hey y'all. Today we'll be looking at question 3 of 2026 Princeton University SciAlly Astro exam. Let's get into it. So it says that this astronomer has found a planet similar to Pluto, and let's see, we've discovered a distant object, SciAlly 26. It's far away, so we can't resolve it, but we're going to find its albedo and radius. And we assume that the system has a uniform surface temperature. So a reason that they mention the resolution part is that if it's resolved, you can measure its like linear distance using like some trig. But here we're going to figure out the radius through a different way. So the first thing the problem says is that it's on a circular orbit of radius a around the sun. So draw our sun here. Circular orbit of radius a, and here is our little planet. The sun has a temperature T sun and our sun. Cool. The object reflects a to space, fraction a to space, and absorbs 1 minus a. That's the albedo parameter. So we're going to assume that the surface temperature is uniform and calculate its equilibrium temperature. So the way you go about these problems is two things. You have to consider P in and P out, which is the net energy going into the system and the net energy going out. And you want to equate these in the condition of equilibrium so that it's at some net consistent temperature. So for Pn, the power going into the system, you could think of it as I have some planet here and sunlight is hitting the surface of the planet. So it's going to hit a cross-sectional area of pi rs squared. So it's going to hit that cross-sectional area, and how much light is being hit per square meter? Well, that's going to depend on the flux that the star is giving to the planet. So that flux is going to be characterized by the solar luminosity divided by 4 pi a squared, where a is the distance from the sun to the planet. And then this is the luminosity of the sun. So you might want to do some review on flux if you don't understand where this is coming from just yet. But no stress. Okay, and so that should be the net power into the system. And what we want to do is we want to characterize the net power out. Oh yeah, this is also going to be modified by some albedo parameter. And that's because this is how much sunlight we're absorbing, the 1 minus a, whereas a is the amount of sunlight that's being reflected out to space. And now we need to characterize how much energy the planet's emitting outwards. That's going to be given by the Stefan-Boltzmann law, which goes as this. It's going to be proportional to the surface area times the energy emitted per unit area, which is given by this Boltzmann formula here. So that's the power that's going out of the system, and we're going to equate these two. So we're going to have pi rs squared L sun divided by 4 pi a squared. 1 minus the albedo is equal to 4 pi rs squared sigma TEQ to the 4th. There's some nice cancellations in that there's no area dependency. So this will go away. Let's see here. Okay, that's fine. Nothing else cancels just yet, but what we usually do, in this problem at least, is you want to note that the sun luminosity can be written like this. 4 pi r sun T sun to the 4th times the Boltzmann constant. So if we put that in, we're going to end up having, I guess the way to make this minimum rewrite here is to move this to the left and then put this expression here right there, just for visualization purposes. And now the cancellations are a little bit nicer, because then you have these 4 pi's go away, these sigmas go away. Okay, cool. So then with that, it looks like what we're left with is this here. These are the solar parameters, 1 minus the albedo over 4a squared is equal to, let's see, TEQ to the 4th. Okay, so that's what we're left with. I brought this 4 here to the denominator, and I canceled out this 4. So that looks like the same form as the equation we were given. We have the 1 minus albedo, r 2a to the root. Yeah, so this is the same form. We would just take the 4th root here of both sides, And you can see if we take the fourth root that this is going to go to 1/2. This is going to go to 1/2 too. Yeah, if you take the fourth root, you'll get the same thing, because like this will go away, this will go to 1/4, this will go to 1/2, this will go to 1/2, and then 4 to the fourth root is the same thing as root 2. So you'll get the same equation as you do here. So that's good. That's the first part. So we were able to derive the relation this relation right here. Cool. So now let's go on to the next. This is a standard planetary equilibrium temperature derivation. Should be pretty common to see in astrophysics. So the next question is that we want to use Wien's law to determine Psi 26 equilibrium temperature. So we're given a few properties here. Information. Here we're given the distance away is 100 AU. So that's going to be our A parameter. Here we're given the visible light spectrum is entirely reflected sunlight. Okay, that's pretty important to note. That'll be relevant to this problem. And its infrared spectrum is near black body. Okay, cool. The flux peaks here. So you can use Wien's law to calculate temperatures. So that's what's going to be relevant here. The other information we're given is that its apparent magnitude is 17.34. And we're going to assume the sunlight side reflects light equally in all directions over half the celestial sphere. So I'll draw what this looks like later for when we need it, and then we have a calibration parameter here. So these parts will be relevant in the next step of the problem. So for now, all we need to do is use Wien's law. So it's T peak. This is the general form for Wien's law. It's the temperature related to the peak brightness, or peak wavelength. That's about equal to 3 times 10 to the negative 3 meters a Kelvin divided by lambda peak. So we're going to have 3 times 10 to the negative 3 meters Kelvin divided by 141 micrometers. And we can write this in meters as 10 to the negative 6 meters. So the meters cancel out, and we're just left with Kelvin, which is what we wanted for units. And this here is equal to, I believe, 20 Kelvin. Let me double check that that's correct. Yeah, about 20.6 Kelvin. 20.6 Kelvin. The actual prefactor for Wien's law should be like 2.898, but 3 is good enough for what we're doing. Okay, cool. So, moving on to the next step, we found that temperature here, the equilibrium temperature, some type of temperature parameter. Now we're going to use the temperature to solve for the albedo. So we have to insert the numerical values to obtain the raw albedo value. So that looks like we're going to be applying this equation from earlier, that TEQ equals 1 minus albedo to the 1/4 R sun divided by 2A. This should be to the 1/2, and then T sun. Cool. So then rearranging this algebraically, not too complicated, you get that, let's see, something like this. Excuse me. You should have something like 2A over R sun, and then let's make these correct. A squared equals 1 minus albedo right here. So that looks right to me. Yep, that looks good. And then you can just invert this really quick to get albedo equals 1 minus this right here. And then we should plug in the values. So if we plug in the values here, we're going to find 1 minus, now your equilibrium temperature we found was 20.6. Sun's temperature is like around here. So this is fine. You're going to multiply it by 4. So what you need to put in here is, might be a little bit easier if we do it like this. Write it here. Here we're going to put in the orbital axis, which is 100 AU times 1. Let me make this a little bit easier to read. So the orbital axis here we found was 100 AU from we were given in this part of the problem. So then 2 times 100 AU times this many meters per AU. That's the conversion there. And that looks fine. We're going to square it and then divide by the solar radii. I think this is 8 meters. Okay, so using this information, you should find that the albedo is like around 0.7. On my laptop right now, I have 0.73. So around that value for the albedo, which means that, let's see, we're actually only absorbing 30% of sunlight, and we are reflecting 70% of sunlight into space. Reflected, which is kind of crazy, but yep, that seems about right. Absorbed. Okay, so next part of the problem, we're almost done. So this question's a little complicated. Let's read through it. Find the total power of sunlight that is reflected and the corresponding visible light flux that we receive here on Earth, and then obtain an equation for the radius RS for Sally 26. So if you're going through this question, I found this one pretty tricky because like it's 3 things we were told to find. So it's honestly kind of a hard question. I think maybe it could have been set up better. But in either case, let's do it. So then find the total power of sunlight that is reflected by Sally 26. So let's see. So you're going to have your sun here, and it's going to be emitting light on your planet. And your planet is going to reflect out some portion of light, which is albedo times, like, it's going to be P out, is what we call it, P reflected maybe. And it's going to be equal to some albedo times whatever sunlight it's receiving, right? And so we're going to do the same exact calculation as before, where it's going to be, we hit a cross-sectional area. That cross-sectional area is going to be pi rs squared. We're going to be striking a cross-sectional area with an energy, like a flux in energy per area of the solar luminosity divided by 4 pi a squared. So this is the same thing as before, is that the energy per unit area over the spherical, spherical shell is going to be its luminosity divided by 4 pi a squared. So that's kind of the idea there. And using that, let's see, this is going to be your P reflected right here, your reflected power. It's going to be equal to the albedo pi r squared solar luminosity divided by 4 pi a squared. So that's that expression, and obviously I guess the pi's cancel. So that's the first part of this problem, is to solve for the reflected power. Now this is the amount of reflected light that the planet is emitting, like strictly reflected solar sunlight. So let's see, light that's reflected and the corresponding visible light flux that we receive here on Earth. So that is let's see, visible light flux. Okay, so we were told in the earlier part of the problem that it says here, assume the sunlit side reflects light equally in all directions over half of the celestial sphere, which is 2 pi a squared. So if we're observing on the planet, if it emitted over the entire celestial sphere, it would take this reflected light and reflect it in all directions like that, right? And so that's going to be a reflection on 4 pi r squared for the entire celestial sphere. But in this case, this planet is only reflecting on the sunlit side. So it's going to be reflecting strictly in this way. So because of that, it's only going to be across like 1/2 of the total celestial sphere, which is going to be equal to 2 pi r squared. So what this is telling us is that the flux that we would receive on Earth. So yeah, let's make this a little more clear. If we have a planet here, it's going to be taking sunlight from the sun, and then we'll put the Earth right here. This is the Earth here, sun here. This light is going to be reflected back in all directions, but we're going to get some portion here on Earth. So that portion is going to be, this is how the factor goes, is that F Earth, the flux on Earth is going to be equal to P reflected divided by 2 pi a squared, which is that half of the celestial sphere comment, noting that, like, you know, our planet's here, planet, P for planet, Earth is here, so this distance is about 100 AU still. 199 AU, about the same thing in this case, in the problem. So that's the flux that we would get on Earth. And then we're going to do this algebraically. It's just going to be albedo RS squared L sun divided by 2 pi a to the 4th, where we're dividing by this factor, putting it here. And this would actually be an 8. So all we did is take the 4a squared multiplied by the 2 pi a squared and put it in the denominator to reflect our division. So that's cool. And then last thing, all you have to do is, the last part of the problem is obtain an equation for RS. Well, that's not too bad. That's just going to be algebraically rearranging this equation here. So then we can have that RS is equal to the square root of 8 pi a to the 4th F Earth. And then we're going to divide by a times the solar luminosity. So that's just algebraic rearrangement of this equation, solving for RS. So yeah, that should give you your radius of the planet. So the last part of the problem is that given its visual magnitude, calculate the light flux that we receive on Earth, and then calculate the radius of the planet. So we were told earlier that the flux, we have this flux scale calibrated here. So here we were told that the magnitude is 17.34. That's the magnitude of the planet, and we were given this flux scale here. So we can get the flux through that, and then we're going to use this equation here to get the radius of the planet. So first off, we want to solve for flux. The way that magnitudes and flux are related goes according to this equation. It is magnitude 1 minus magnitude 2 equals negative 2.5. Sometimes you'll write 2.512, but in this case just do 2.5 log 10 of F1 over F2. So that's the general equation. So in this case we have, plugging in our numbers, we have 17.34 for the planet minus our Vega, which is like our reference planet, reference star, negative 2.5 log 10 of F1 divided by the flux of Vega, which was stated to be, Vega's flux was stated to be 3.1 times 10 to the negative 9. So 3.1 times 10 to the negative 9 watts over meters squared. So what we would do is just solve for this right here, divided by negative 2.5 equals 10 to this number. It's going to be equal to F1 divided by 3.1 times 10 to the negative 9 watts over meters squared. So we can solve this equation to get that F1 is, let's see, it's about 3.6. F1 equals 3.6 times 10 to the negative 16 watts over meters squared. So that's the flux that the planet is giving us at Earth. And then the last thing we have to do is calculate the radius. So we're just going to plug in all our values from before. I'm going to erase this. Plug in all our values from before, that RS is equal to the square root 8 pi 1.5 times 10 to 11th meters AU times 100 AU to the 4th times 3.6 times 10 to the negative 16th watts meter squared. And then divided by, is that right? Yeah, that is right. And then divide by 0.73 for the albedo times the solar luminosity of this. This is solar luminosity. And yeah, this looks about good. You can do a quick units check, and that watts cancels, and then this will give us the square root of meters to the 4th times 1 over meters squared from this and this, which is the same thing as root meters squared or meters. So the units are good. And RS is going to be equal to about 1,300 kilometers. Make sure you'll get an answer in meters, so then you have to divide by 1,000 to get kilometers. And for context, this is a little bit larger than Pluto. So yeah, thanks y'all for watching. I hope that was useful, and drop any questions in the comments below.